There are moments in astronomy when observation collides with mystery, when the universe whispers something we did not expect, and all our equations tremble. This is one of those moments. In the silence of the solar void, near the point where the sun's gravity burns brightest, an object known as 3I Atlas has done something it should not have been able to do. It moved faster than our physics allows. At first, the data seemed like noise, a measurement error, a calibration drift. But as the numbers solidified, as multiple observatories confirmed the readings independently, the implications began to unfold like the slow turning of the night sky. Something happened at perihelion, its closest pass to the sun, that our models cannot explain. The essence of this story is simple, yet what lies beneath it shakes the foundations of celestial mechanics. We have an object of known trajectory, an interstellar visitor, like the few that have passed through our system before. Its orbit was mapped, its speed predicted, its path traced by the gravitational dominance of the sun. Every law of motion told us exactly where it should be and how fast it should travel. But as the light from perihelion reached our senses, those numbers changed. 3I Atlas accelerated by hundreds of meters per second, defying the pull and precision of gravity. Now, 300 meters per second may not sound like much to the untrained ear. It is the velocity of sound at sea level, a mere whisper compared to the titanic speeds of planets and comets. Yet in orbital mechanics, such a difference is seismic. It is the kind of delta feed that requires thrust, deliberate force, energy directed with intent. It is enough to alter a trajectory across interstellar distances, to turn a path of escape into a controlled arc, to move from being a visitor to becoming a resident of our solar system. That, more than anything, is what has stunned scientists across the world. So what exactly are we seeing? A comet? A fragment of something ancient cast from another star system? Or something built? Something that maneuvers? These questions are not asked lightly. The space science community is cautious, almost reverent, in the face of anomalies. Yet this anomaly has persisted, strengthened, and held true across every observation. The Hubble Space Telescope, ground-based observatories, spectrometers scanning in the ultraviolet and infrared, all recorded motion that does not fit the equations of celestial dynamics as we understand them. The atmosphere of this discovery feels unlike anything since the days of Oumuamua's first detection. Then, too, we saw odd behavior, strange acceleration, unexplained reflections, unorthodox motion. But where that earlier object left questions, 3I Atlas brings data, hard numbers, measured changes, time-stamped events. And all those numbers lead to the same uncomfortable conclusion. The acceleration was real, it was sustained, and it was directed along its path of travel. Not away from the sun as we would expect from sublimating ice and escaping gas, but forward, as though something was propelling it. For decades, scientists have studied the behavior of comets as they near the sun. The heat triggers sublimation of frozen volatiles, carbon dioxide, water, ammonia, and the gas escapes, creating the familiar glowing coma and the tail that stretches away from the star. This process can create small, irregular accelerations, natural thrust from jets of vapor. We know this. We have equations that describe it. But 3I Atlas does not match those equations. Its outgassing, if any, was modest. Its coma did not expand dramatically. The spectral lines we expected from strong gas release were faint, and yet its motion told a different story. Something powerful was pushing it forward. The implications unfold in waves. If this acceleration cannot be explained by natural processes, then something else is at work. It might be an exotic mechanism, an interaction we have not yet modeled, some previously unknown property of volatile materials reacting to solar flux. Or it might be Deliberate? Propulsion? Control? The very word feels strange when applied to a piece of rock or ice adrift between the stars. But when numbers whisper intent, when trajectories change at precisely the most efficient moment, our understanding must stretch. At this stage, we are standing at the edge of knowledge. The data are clear, the cause is not. Some scientists urge patience, reminding us how easily excitement can outpace evidence. Others sense a turning point, a moment when we must entertain possibilities that once belonged only to fiction. In astronomy, extraordinary claims demand extraordinary proof, but proof begins with anomalies like this one. Something happened at perihelion, something powerful, something that might not be natural. And in the coming minutes, as we trace the data, the mathematics, and the silence between the stars, we may find ourselves staring at the first signs of a truth we have long suspected but never confirmed. For now, what we know is this: 3i Atlas came closer to the sun than at any point before, and in that narrow corridor of cosmic fire it changed. It moved with purpose, and in doing so it changed us, forcing us to look again at the heavens we thought we understood. Whatever happened there, in that furnace of light and gravity, did not merely bend its path. It bent the boundaries of what we believe is possible. When the first telemetry came in from the solar observation arrays, the data analysts thought it must be an artifact, an interference pattern perhaps, or a calibration drift caused by solar flare activity. The acceleration readings for 3i Atlas did not match the predictions from the standard gravitational model used by NASA's Jet Propulsion Laboratory. According to every equation known to celestial mechanics, the object's velocity during perihelion, its closest approach to the Sun, should have followed a curve governed solely by the mass of the Sun and the momentum carried from its interstellar entry. Yet the numbers showed something profoundly different. At a heliocentric distance of 0.7 astronomical units, the object gained an additional 300 meters per second, a precise and sustained thrust perfectly aligned with its direction of travel. The first confirmation came from the Solar and Heliospheric Observatory, which recorded a faint but measurable deviation in the predicted path. Then came corroboration from NASA's Parker Solar Probe, whose instruments, though not designed for long-range tracking, picked up the subtle shift in trajectory. When the European Space Agency's solar orbiter transmitted its own data, the anomaly could no longer be dismissed. The acceleration was real, measurable, and consistent across independent platforms. This was no instrument error, no sensor artifact. The universe was telling us that something had acted upon 3i Atlas. To understand why this is so astonishing, one must consider the mathematics behind it. In orbital mechanics, motion around a star is governed by Newton's laws, and more precisely, by the conservation of angular momentum and energy. For a body of roughly 400 meters in diameter, the estimated size of 3i Atlas, to change its velocity by 300 meters per second without external forces, the energy involved would be staggering. Calculations showed that to achieve such a delta 5 through natural outgassing, the object would need to expel nearly 60% of its total mass at a velocity typical of sublimating gases, around 500 meters per second. Yet observations from the Hubble Space Telescope, from ground-based optical arrays, and from infrared spectrometers revealed no evidence of such massive ejection. The coma, the luminous halo of gas and dust that surrounds active comets, remained faint and stable. Spectroscopic lines indicated moderate activity consistent with ordinary solar heating, nothing approaching the magnitude required for this acceleration. This discrepancy sent ripples through every observatory on Earth. The International Astronomical Union convened emergency sessions of its Minor Planet Center, and teams at Caltech, the European Southern Observatory, and Japan's Subaru telescope began reanalyzing every recorded photon from the perihelion passage. As the data accumulated, the conclusion only deepened. The acceleration was not random, and it was not radial. It was vectorial, oriented precisely along the object's velocity path. In other words, it did not push the object away from the sun, as would be expected from sublimating ice reacting to solar radiation. It pushed it forward, as though something aboard 3I Atlas was deliberately increasing its speed. NASA's official statement was cautious. They proposed asymmetric outgassing, a phenomenon seen occasionally in comets with irregular surfaces. In theory, if a volatile, rich cavity opened on one side of the object and vented gas in a direction aligned with its motion, the result could mimic propulsion. But this explanation faltered under quantitative scrutiny. The amount of gas required would produce visible plumes, large-scale coma expansion, and spectral emission lines that would dwarf those observed. Moreover, asymmetric outgassing tends to occur intermittently, not with the smooth precision recorded here. The acceleration built up gradually over approximately 18 hours, reached its peak within 2 hours of the exact perihelion point, and then declined over the next 12 hours. A total of 30 hours of sustained force. That pattern mirrors a controlled thrust curve, not a random natural venting process. Astrophysicists at the Harvard-Smithsonian Center for Astrophysics modeled alternative possibilities. Could solar radiation pressure have played a role? The answer was unequivocal. No. The mass-to-area ratio of the object was far too high for photon pressure to produce anything beyond a negligible drift. Could the acceleration be caused by tidal fragmentation, an internal redistribution of momentum as the object cracked or split under solar stress? Again, the observations refuted this. The light curve of 3I Atlas remained stable, showing no abrupt variations that would signal fragmentation events. It did not tumble chaotically. It moved with quiet precision, as though guided. Some researchers drew parallels to the Oumuamua event of 2017, another interstellar visitor that displayed unexplained acceleration. But where Oumuamua's data were fragmentary and its shape irregular, 3I Atlas offers far clearer evidence. Radar mapping from planetary defense arrays has revealed a relatively uniform ellipsoid, approximately 400 meters along its major axis and 280 meters across its minor. Its rotation period, measured at 11.7 hours, remained stable throughout perihelion. The thrust signature, however, showed no modulation corresponding to that rotation. If outgassing were the cause, one would expect the thrust vector to oscillate as the vents rotated into and out of sunlight. Instead, the thrust remained constant relative to its trajectory, smooth, directional, unwavering. The pattern became even more intriguing when researchers noticed its timing. The acceleration peaked within 2 hours of the perihelion, the very moment when changes in velocity produce the greatest effect on future trajectory. In spacecraft navigation, that window is known as the optimal burn window, where a brief impulse yields the maximum alteration in orbit. For the acceleration of 3I Atlas to coincide so precisely with that moment defies probability if the cause were natural. It mirrors the kind of precision one would program into a navigation algorithm. This led to an even deeper mystery. Post-perihelion tracking showed that the object's trajectory had shifted. Before the event, its predicted path indicated it would exit the solar system along a hyperbolic arc, crossing the plane of the ecliptic and heading toward the constellation of Pegasus. After the acceleration, new orbital solutions placed its outbound course several degrees lower, passing closer to the orbit of Mars. The difference may seem slight, but in astronomical terms, it is immense. Over 100,000 kilometers of deviation at the point of closest approach. The new projection shows 3I Atlas will pass within 160,000 kilometers of Mars, well inside the orbit of Deimos, Mars's outer moon. That proximity has ignited global attention. The Chinese National Space Administration, already operating a long-term Mars mission, quickly adjusted the trajectory of one of its observation probes to align with the predicted flyby window. Their strategy is elegant. Rather than chase the object directly, they intend to let it come to them, using Mars's gravitational field to bring the object within observational range of their instruments. Meanwhile, NASA and the European Space Agency are assessing whether any of their Mars orbiters, Mars Reconnaissance Orbiter, MAVEN, or the veteran Mars Express, can be repositioned to capture data during the flyby. Each maneuver, however, requires fuel, and fuel is life for an orbiter. Every course correction shortens mission duration. Yet the potential knowledge gain is enormous. The physics community now finds itself caught between skepticism and wonder. Could an object from another star system, roughly 400 meters wide, truly possess propulsion? If so, what kind? The simplest explanation would be some form of outgassing driven by volatile compounds we have not yet catalogued. Perhaps materials with much higher exhaust velocities than water or carbon dioxide. But to achieve the observed acceleration, the exhaust velocity would need to exceed 5,000 meters per second, an order of magnitude higher than any known natural sublimation process. That range lies firmly in the domain of engineered propulsion, ion drives, chemical rockets, or nuclear thermal engines. When engineers at the European Space Operations Center ran back calculations on the energy profile, they discovered that the acceleration curve resembled a low-thrust, high-efficiency burn similar to what human spacecraft use when operating ion propulsion systems. The gradual buildup, the sustained plateau, the gentle decline, all matched the characteristic pattern of power-modulated electric thrusters. If this were natural, it would be the first naturally occurring phenomenon ever observed to mimic engineered propulsion so precisely. The theoretical implications are staggering. If the acceleration is natural, we are witnessing a process never before recorded, perhaps a form of sublimation involving exotic volatiles or dust plasma interactions near the solar corona that create directional forces. Understanding such a mechanism would rewrite the physics of cometary dynamics and force us to reconsider how small bodies behave under extreme solar radiation. But if the acceleration is artificial, then we are confronting something much larger. Evidence of controlled movement, possibly the first indication of a technological artifact of non-terrestrial origin. As the debate intensifies, radio telescopes across the globe have turned their dishes toward 3I Atlas. The Allen Telescope Array, the Very Large Array in New Mexico, and the Meerkat Array in South Africa have begun synchronized observation campaigns scanning across radio frequencies from megahertz to gigahertz, searching for structured signals, patterns that might betray communication or data transmission. So far, the results are silent, filled only with the usual cosmic background. But silence itself can be deceptive. If the object possesses a transmission system beyond our understanding, it may communicate in ways we have not yet conceived. Through modulation or carrier frequencies, our instruments are not calibrated to detect. Within scientific institutions, the atmosphere oscillates between disbelief and restrained anticipation. Theoretical astrophysicists draft papers late into the night, crafting equations to reconcile the impossible. Planetary defense teams quietly update contingency protocols, considering what actions might be taken if the object alters course again, particularly toward Earth. Meanwhile, in laboratories from Pasadena to Munich, engineers simulate the perihelion acceleration in virtual environments, testing every conceivable natural mechanism: trapped volatiles, rotational venting, even electrostatic interactions between solar plasma and the object's magnetic field. None reproduce the observed thrust without invoking implausible parameters. And yet, the caution remains. The burden of proof in science is unforgiving. A single unexplained acceleration does not constitute evidence of extraterrestrial technology. It may be an exotic natural phenomenon, a discovery that will expand our knowledge of astrophysical chemistry rather than rewrite civilization's place in the cosmos. But the closer the analysis grows, the harder it becomes to ignore the precision, the timing, the directionality, traits that echo intent. Every simulation returns to the same unsettling conclusion. To replicate the observed motion without implausible loss of mass, the ejected material must travel at velocities thousands of meters per second faster than any natural outgassing. That implies machinery or an energy source buried deep within the object's structure, releasing thrust in a controlled pattern. In either case, 3I Atlas defies classification. Now, the world waits for Mars. 93 days after perihelion, the object will pass through the Martian neighborhood, within reach of high-resolution cameras and spectrometers. If it performs another acceleration, even a subtle one, the mystery will deepen beyond denial. If it remains steady, perhaps we will attribute the perihelion event to an extraordinary but natural process. Either way, the data gathered during that flyby will echo across decades of scientific research. The silence between the stars has never felt so full of questions. Something at perihelion changed 3I Atlas, and in doing so, changed us. The laws of motion we trusted have been challenged. The boundaries between the natural and the deliberate have begun to blur, and as telescopes pivot toward Mars, humanity stands at the threshold of an answer that could redefine everything we believe about our place in the universe. To understand the weight of this moment, we must step back and look at the long arc of humanity's relationship with the unknown. Every generation of astronomers has stared into the darkness, searching for meaning, chasing faint movements of light against the endless backdrop of space. From Galileo's trembling sketches of Jupiter's moons to Hubble's first deep-field image that revealed galaxies like grains of sand, we have always been explorers of patterns, seeking order in the vast, indifferent cosmos. But now, with 3I Atlas, we find ourselves facing a pattern that does not belong to randomness or natural law as we understand it. Something about its precision, its deliberate rhythm, evokes not chaos, but purpose. The story of this object begins far beyond our system, somewhere in the abyss between the stars. When it was first catalogued, its hyperbolic trajectory told us it came from interstellar space, an emissary of another region of the galaxy, perhaps even another stellar nursery long extinct. Scientists labeled it with the prefix I, marking it as interstellar, the third such visitor recorded after Oumuamua and Borisov. Yet while those earlier travelers passed silently through, obeying the quiet elegance of celestial motion, 3I Atlas broke the symmetry. It did not simply visit, it interacted. At the heart of this investigation stands the instrument that has become the eye of modern astronomy, the Hubble Space Telescope. Even in its advanced stage, Hubble's optical precision remains unmatched. During perihelion, it captured continuous imagery of the object, revealing subtle variations in albedo across its surface. Patches of brightness that seemed to pulse, not randomly, but rhythmically. Initially dismissed as rotation effects, these fluctuations became the subject of renewed scrutiny when the acceleration data emerged. Analysts noticed that the timing of the albedo changes corresponded loosely to the rise and fall of the object's thrust curve. Could those brightening phases be linked to the emission of energy, perhaps from venting or from something more complex? When the James Webb Space Telescope turned its infrared instruments toward the fading trajectory weeks after perihelion, it detected faint residual emissions inconsistent with standard cometary activity. The heat signature was localized, not diffused across the surface, and decayed in a pattern resembling the cool-down of engineered material rather than the slow thermal release of natural ice. The data remain preliminary, but they have intensified an already growing debate about what kind of matter constitutes this enigmatic traveler. Its spectrum suggests compounds unfamiliar to typical cometry models, silicate blends with unexpected metallic ratios, reflective properties hinting at highly ordered crystalline structures. None of these characteristics match the expectations for an inert chunk of rock and ice adrift through the void. But the object itself is not the only story here. Behind the data are the people, the scientists whose lives have been consumed by the pursuit of understanding this anomaly. Dr. Elena Sato, a propulsion physicist at the European Space Agency, describes the perihelion event as a test of humility. Her team spent months attempting to reproduce the observed acceleration through natural processes, but every model failed. When she speaks of the experience, her tone carries both awe and unease. "We are looking," she said in a recent interview, "at something that acts as if it knows the laws of orbital mechanics as well as we do. Perhaps better." Across the Atlantic, at NASA's Goddard Space Flight Center, Dr. Marcus Wren compiled the comprehensive perihelion dataset, cross-verifying readings from more than a dozen observatories. He was the first to notice the 30-hour thrust curve aligning perfectly with the predicted optimal burn window. For Wren, that discovery was both exhilarating and unsettling. "In orbital navigation," he explained, "you plan burns at perihelion because that's where they matter most. The math is elegant, efficient. 3i Atlas executed that maneuver with textbook precision." His voice paused in the interview recording, the silence heavy before he added softly, "But it shouldn't have known." The object's composition, shape, and motion are still under intense examination. Radar reflections suggest a structure with unusually smooth surfaces, not the jagged, chaotic contours typical of natural bodies of similar size. Some scientists have speculated it might be coated with a reflective material, possibly metallic, possibly something beyond our classification. When light from the sun struck its surface during perihelion, polarization analysis showed an angle of reflection consistent with highly uniform layers, perhaps panels or plating. If true, that would imply design. Yet even among those who dare to entertain such hypotheses, caution reigns. The scientific method demands skepticism, and speculation must never outpace evidence. Many continue to argue for exotic natural explanations, forms of volatile outgassing triggered by microfractures, electrostatic interactions, or plasma effects induced by solar magnetic fields. But as the community awaits the Mars flyby, the line between skepticism and curiosity grows thinner with each new dataset. The upcoming Mars encounter has become a planetary-scale collaboration. Instruments on NASA's Mars Reconnaissance Orbiter have been recalibrated for high-speed tracking, while ESA's Mars Express is executing a minor orbit adjustment to maximize its observation window. Even the Perseverance rover, resting on the Martian surface within Jezero crater, will aim its skyward sensors during the predicted pass, ready to capture faint optical or radio anomalies. The global coordination behind these efforts echoes the spirit of the early space age, a collective reaching outward, beyond competition, driven by wonder and the shared pursuit of knowledge. Beyond the instruments and equations lies a deeper current, the realization that if the acceleration of 3I Atlas is truly the result of propulsion, then this marks the first evidence of technology not born on Earth. It would mean that somewhere, perhaps light years away, another civilization mastered the principles of motion and energy we have only begun to grasp. The implications ripple across every domain of human thought: astrophysics, philosophy, even theology. What would it mean if we are not alone, and not merely accompanied by microbes or simple organisms, but by intelligence capable of traversing the stars? For those working closest to the data, this thought hovers at the edge of every conversation, never spoken too loudly, yet never far from mind. There is reverence in their restraint, a recognition that evidence must lead emotion, not the other way around. And yet, in quiet moments, even the most disciplined scientists admit a sense of awe. Dr. Sato described standing outside the observatory one night, watching the faint streak of 3I Atlas through a telescope, realizing she was witnessing something that might alter humanity's story forever. It felt, she said, as if the sky was looking back. The possibility that the object may maneuver again near Mars keeps teams awake across continents. If it performs a deceleration burn using the planet's gravity to capture itself into a solar orbit, it would confirm the existence of controlled flight. Such an event would transform not just astronomy, but our understanding of civilization's place in the cosmos. Even if the object continues outward, maintaining a purely hyperbolic trajectory, it will still have left a permanent mark. The mystery of its acceleration will remain a catalyst for decades of inquiry, inspiring new generations of researchers to question the limits of physics and the nature of intent itself. History reminds us that every great discovery begins as an anomaly. Uranus's irregular orbit led to the discovery of Neptune. Mercury's orbital precession led to Einstein's theory of relativity. Now, the unexplained acceleration of 3I Atlas may lead us toward a new understanding of motion, energy, or perhaps consciousness in the cosmos. Whether we uncover a natural process more exotic than any we've imagined, or the first evidence of an intelligence that predated us by millennia, the outcome will redefine what it means to be human. In the grand narrative of exploration, this moment feels like the opening of a new chapter, a slow, trembling page turning beneath the weight of starlight. We do not yet know what 3I Atlas is, or what it represents, but we do know what it has already achieved. It has united scientists, philosophers, and dreamers under a single question that transcends language and nation. What moves in the dark beyond our understanding, and what does it want us to see? The countdown to the Mars encounter continues. Observatories hum through the night, algorithms run endlessly, and deep within humanity's collective curiosity burns a sense that the universe is on the verge of speaking again. Perhaps what we are witnessing is not an arrival, but an invitation. To see the cosmos not as a cold expanse of matter, but as a place of intention and design. When future generations look back on this time, they may remember the day our instruments recorded an impossible acceleration near the sun, and the way that single event reshaped our perception of existence. They will remember the scientists who dared to ask if propulsion could exist without engines, if intelligence could travel without words, if the void itself could send a message. And they will remember the name that marked the turning point, 3i Atlas, the object that came from the stars, moved when it should not have moved, and left us with the most human question of all. What if someone out there saw us first?